Hello and welcome to the Characters, Image and Sound live stream. I hope you are all well. Please do welcome yourselves. That makes no sense. Say hello in the comments or say something so I can welcome you to the stream. And hopefully I'm talking to not myself today. I've clicked on the right button, not tried to go back and do a stream from a week ago, which was slightly embarrassing. But there we go. I hope all is well. Please say hello in the comments. I've got a new update on this thingy, so hopefully I'll be able to see your comments. There we go. I should be able to see those there. All right, good. So I hope you're all well. I hope you're doing better. The weather is slightly nicer than it was, which helps a bit. So please say hello to make sure I can see Josh is here. Hello, Josh. How are you doing? Thank you for coming along. It is great to have you here. Please say hello. That's a relief because I spent the first few minutes wondering if I was going mad last time. But, well, in spite of that, I'm glad you're here. Right, so let's have a look at what we're going to do today. So we've got characters, image and sound. It's a big topic in paper one. And there's a kind of principle that runs through this topic, which is binary numbers, that everything that can be represented on a computer is represented in binary numbers. And that is something that gets carried through. Manure, how are you? Thank you for coming. Good to see you. Yeah, so that's what we're going to do. Let's do a quick rewind first of all and see if we can pick up any of this stuff we covered before. So this is the amazing game of Guess the Question. So here is the answer, and I keep picking on this one because I reckon it's going to be in the exam, and it's a topic that people find a little bit abstract because it's kind of it's memory, but then it's slightly more abstract than memory. What's this one all about? What could the question have been? The answer is more RAM and PC performance, speeds up access to data, excessive use of VM, which is the giveaway here. Can cause disk thrashing. This, by the way, is from a past paper, which is why I've picked it up. Which decreases performance, VM slower to access than RAM directly, moving data between RAM and PC takes processor time. Any idea what this is all about? What do you think the question may have been? What do we think? Any idea at all? What do you think? Well, I shall break it to you gently. The answer was something around explain why it's beneficial to get more RAM instead of using virtual memory. The story here is virtual memory is when your RAM is full and the CPU uses part of your hard drive as RAM, and the hard drive has got a slower read-write speed, and obviously what the CPU can't talk to the hard drive directly. It has to go through RAM because RAM is primary memory and your hard drive is secondary memory. So therefore it takes longer and it's slower and it's far more likely to ruin your hard disk, because the hard disk is designed to be written to and read from, but not as often as RAM, which is designed to be read to and written from all the time, okay, or far more regularly. So let's have a go at this one. Any idea? Can you guys name any of these registers? What do we think? We've got stores address where data will be read. So stick a letter and then write down what you think the register may have been. And I put this in there because they love a bit of registers. OCR will definitely do something on registers when it comes to the exam. What do we think? What about the first one? That address, that might give you a clue. And what about the second one? Data. There's only one data register that we need to worry about that's got a D in the title. Ooh, hello Pablo. Good to see you. Now this is quick. Pablo's gone for MAR, a good guess because the A is address. MDR for B because the data is a D. The result of a calculation is the ACC, which is the accumulator, spot on. And D, I think we have to go for applause for Pablo because he's got it all sorted out. So this is what it should be. And just make sure you're happy with those. It's quite an abstract and difficult thing to remember, but if you can do that, you will get some good marks for this. Okay, next one. Can you remember doing a logical shift left, a very difficult thing to say, does what to a binary number? You've got a 50-50. What do we think? What does left do? Does left divide or does left multiply? What do you think? It is Jeopardy. Josh has come in with multiply. It's a 50-50. Should we see, Josh? You are absolutely spot on. It is indeed multiply. Okay, we're on fire now. Hopefully not literally. Doing a 2-bit left logical shift has what effect? Is it by 2 or is it by 4? The stress. What do we think it could be? So Pablo has gone for multiply. I'm taking it. He said B. Multiply the number by 2. Josh has gone for D. Multiplies the number by 4. All the bases are being covered here. Shall we see what it comes up with? The correct answer is that this is doing something quite strange. Let's try that. Yay! It multiplies the number by 4, which meant that D, it was Josh who was the correct answer. Outstanding. Well done, Josh. Good effort. Okay, let's push on. What is it all about? So now we're going to jump in and do the learning today. I've tried to condense this, and I've realised I haven't sent you the PDFs from the past live streams, which I will do after this. I've got them all queued up, so I'll put them on Satchel 1 after this live stream. Right, so we are still inside memory and storage. This is a screenshot from the specification, which is a jolly handy document, I can tell you. And this is what we're going to cover today. About what? Oh, that was the previous question. My humble apologies, Pablo. Multiplies by 4. Sorry, I should have given you. I take it all back. If I'd scrolled down, I could have seen that you were correct. I should have known better. So these are the 3 areas. This is the representation sort of area where how does a computer represent these 3 different things, as in characters, images, and sound. All right. If you think about it, a video file is a combination of probably all 3. Characters, we're talking about words and text documents and so on, and about printing on screen. And images are, well, images. So we're going to look at these. The use of binary codes, the term character set, we'll jump in and have a look at it. Look at the 2 different character sets you need to understand, ASCII and Unicode. One can hold more characters than the other. And then how an image is represented with pixels in an image, about metadata, and about resolution. And then we'll look at bit depth as well. And then sound, we look at how you can, and by the way, how to calculate these different file sizes as well. We'll have a look at that. So there's quite a lot to cover. And there are some terms that you need to understand in here, as ever. You don't need to memorize the character sets. That's something that's quite important. You don't need to do this. Decent, dear man, how are you? You've only missed the entrée, so we're only getting into the sort of the meat of it now. Well, I think we've got 8 people online now, so that's great. Do say hello if you're there. What else have we got? So that's what we're going to do. So this list of what you do and don't need to do, all the stuff I've said we need to do, but we don't need to memorize the character codes because that would be madness. Now, I've rather optimistically called this a 5-minute teach. I think it's more like a 10 or a 15-minute teach, but let's see how it goes. As I said to you, I've tried to condense all of this into as little on the page as humanly possible. So first of all, characters. The very first thing and the most important thing that for 1 mark they're going to be looking to get you to establish or to show you understand is that computers only understand binary. The word understand is rubbish. I'd use the word parse, which is, let's write down parse for you. It would be spelt like this, P-A-R-S-E. That would be parse. That should be the word. But the word understand is kind of fine because we know what we mean, right? Computers only work with binary. That's what they understand because and if you remember last time, computer circuitry only has 2 states, on and off, and that can easily be represented by 1s and 0s, binaries. That's why. So therefore, the logic is that we're going to look at characters, images and sound, And obviously, if computers can only understand binary, then images, characters, and sounds also have to be represented in binary. Now, I want to show you Exhibit A. Now, this is not a reason to flex about my mechanical keyboard, although I have to say, I balked at the idea. You like my little dog on it? I'm very pleased with the little dog. Let me show you the little dog there. See the little dog? It's a border terrier. Oh, it's gone away again. There you go. So this mechanical keyboard I absolutely love because it makes a nice clickety clicking sound when you use it. There's something that is important to remember, and that's that we think about the characters right on the keyboard, but what about this one here? Can you see it? This is the space bar, that big one there. Now the space bar is here actually. Now the space bar, you could say, well, the space bar is not a character. Well, it's a blank space, but it's still a character in that it has to be represented, as do the comma, the asterisk, the pound sign, the euro, the brackets, all the rest of it. Yes, thank you. Do you know, I'll take that. I spent far too many hours researching this keyboard, and I thought, oh, I'm spending money on a keyboard, and you forget you interact more with this thing than anything else when you use a computer, and it's an incredibly pleasing thing to use, and it makes a lovely clicking sound. Very nice. Anyway, yes, so what's the point I'm making? You've got to represent all the characters. So if you imagine the way this works is that every character has to have its own binary number. A, B, C, D, E, F, G, comma, space bar, all of those. They each have a binary number. They're represented by one binary number. And that is put, and when that's done, it's called a character set. And it's like a table where you've got the character it represents, and then you've got the binary number that's used to represent that character, okay? So there's that translation process that when you hit the space bar, it actually corresponds to a binary number. That's what the computer is using to represent it. And so when you work out a set of those for a whole keyboard or for a language, they are called character sets. So this here, indeed, and to you, dear man, thank you for coming. Good to see you. Now, in terms of the exam, this one here, this was taken directly from a mark scheme. They'll ask you what a character set is. The set of characters the computer can understand. I took that from an OCR mark scheme. So that's what they're expecting to see when they ask you what a character set is. And this first thing I've got up here about computers only working with binary numbers, they often squeeze that in early on in this sort of a question for just to make sure you understand that computers only use binary. And back to that, because they've got circuits which can only have on and off. They've got two states, on and off. Right, so now we're into character sets. So are we happy with this notion that a character set is the way in which the numbers or the characters on a keyboard, the letters, the different, and think about it, you've got different languages, haven't you? Because we've got, obviously we use English, but you've got all the French characters, the E with the accent aigu running up that way. You've got the accent grave, you've got the circonflexe, you've got the SZ in German. But then you've got Japanese and Chinese, and they've got loads and loads and loads of characters and totally different alphabet altogether. So when I was in France writing my dissertation, I had a French keyboard because our keyboard, if you look at the sort of top left, it's a QWERTY keyboard. The French keyboard is an ASCII keyboard, so it's a totally different arrangement, and they've got letters arranged in a different way. Right. So there are two sorts of character sets that you need to understand. Ah d'accord, très bien. Je vais lire ça plus tard, d'accord? Très très bien. That's quite bizarre because I was one of my year 11 students last year. French was his first language, and we used to annoy people by speaking in French sometimes, but it's always good to do that. So we've got two here, right? These are the two you need to understand. We've got ASCII, which is this one here, which looks a lot like it says ASCII. This one here. Can we see that? Yep. And then we've got Unicode, this one here. The key facts are the first one that came out was ASCII. Now, this 8-bit number, this is what we need to understand, right? If you increase the number of bits, you have the ability to describe more things. I'm going to talk about colors in a second. So you were mucking around in Photoshop, may have seen that you can do a color setting with 256 colors, or you can go for millions of colors. But if you go for millions of colors, you're going to be selecting from one of millions of binary numbers. So therefore, those numbers are going to be longer and there are going to be more of them. So you need more data to represent it, right? And you can have more shades. But I'm getting ahead of myself here. So understand the first character set that was released was this one here, the ASCII one, all right? This guy here, 8-bit number, and it can represent up to 256 characters. Now, they may well ask you, well, what is the benefit of using Unicode over ASCII? Well, Unicode is a 32-bit code, which means that you can represent 4 million characters. So therefore, using Unicode, you could represent Chinese, Japanese, Cyrillic, Russian, and all the other languages whose names I don't know. Greek, that's a different alphabet as well. So there's loads and loads and loads of different alphabets out there. So Unicode, it's a larger character set, but it can represent more characters. So you do need to know the 8-bit versus 32-bit. And I don't think you need to necessarily know about 4 million characters, but it helps. So you've got 256 because it's 8-bit. An 8-bit number can represent 256 different things, all right? So thinking ahead, when we're looking at colours, if you've got a palette, and imagine an artist palette, you know, the palette that they hold in their hand and they will draw oil paints from. If you've got a palette with 8 colours on it, you can represent so much. If you've got a palette with 256 different colours, you can represent more colours. Although you could argue you could mix all the different... yeah, let's not get into that. I've talked myself into a hole there. But hopefully that is making some kind of sense. So that is your characters. Let's look at images now. Same thing before. Images represented in binary. They're represented using... So bitmap images are rows of dots that are called pixels. They're not actually dots, they're squares. But squares called pixels. And pixels is short for picture elements. Don't need to know that, but it helps. So each pixel, and if you zoomed in and in and in and in and in and in and in on a picture, you can see that it's made up of squares, right? Those are the pixels. And each pixel is represented by a binary number. So black will have a binary number. Yellow will have, or that shade of yellow will have a binary number. Now, this is where I'm going to jump down and look at color depth, okay? So color depth is the number of bits used to represent each pixel. So you could choose to have a bigger range of, yeah, Ziggy, that's absolutely fine. And just pass it on to people. Just put down my email address for the reference, okay? It's not a problem. And for anyone else, just, of course I'll do your references. Just put me down. It's not a problem. The more colours that you can choose from, the more binary numbers you're going to need to represent. So for example, you could have yellow, or you could have 50 different shades of yellow, no problem. Or you could have 50 different shades of yellow, okay? But if you want 50 different shades of yellow, you're going to have a binary number to represent each of those different shades of yellow. Does that make sense? It does make sense, doesn't it? So your picture will be of higher quality if you're able to represent more different shades of colour in it than if you use fewer. But of course, your photo will get bigger. The file size will get larger. All right, so now let's jump back to this bit that I skimmed over before, which is this. Resolution is, and I almost used the word literally there. That was a very bad bit of drawing again. Let's try that. Resolution is the size of your image in pixels. So width and height of your image. And you know when you download something from the from Google, you've got a choice of going for large, medium or small, and large will be 3,500 or 5,000 pixels across. It gives the width first. That's your resolution, okay? People talk about sensors in terms of their resolution, and that's how many pixels they are able to record. So that is resolution. And we've talked about color depth. You need to know those because the questions that they will ask later on will make sure that you understand what color depth means. And literally for color depth, the number of bits used to represent each pixel, okay? And so if you want to have more colors, you're going to have longer numbers. That's the point. Okay, so if you have more bits, you have a higher color depth, which means you've got more colors and shades. And more colors and shades equals a higher quality image, but means a larger file size. And it's that balancing act. It's that like a seesaw, that if you increase the quality, you increase the file size, which means that it can be harder to send across the network. It can be harder to upload, and that'll take longer to download and upload. You can get fewer of those pictures on your hard drive and so on. And they love a bit of a question about that. Where am I time-wise? I feel like I'm talking too much. 10 to 7. Okay, we're doing all right. Okay, so metadata. Meta is Greek for above. And there'll be people with beards in Brighton coffee shops wearing woolly hats talking about, yeah, it was so meta. And meta means above. So it's like looking down from above. So metadata, if you take a picture, an image with a camera, it's metadata. Look at that bottom option down there. It's metadata will give you further details about the image, like the camera make and model, the aperture, the exposure, all that sort of malarkey. Yeah, no problem, Yusuf. That is what metadata is. So the metadata for a photograph is things like the camera that took it, the model, the size of the image, the aperture, the exposure, the shutter speed, whether the flash was fired, etc., etc. Okay. For images, metadata could represent the color depth, the image height, the width, all that sort of stuff. And for a text file, this is. For a file, it could be the type of file, whether it's a bitmap, a JPEG, whatever, the size of it and the date it was created. Okay, so all of that is metadata. So it's a file, it's information about a file, data about data, which isn't very helpful at the top there, but it's information about a particular file, about some data that's been saved. So that is known as metadata. The other handy thing about metadata is that it can help an app to decide how to open something. So, for example, something saved as a .doc, the CPU will look at it and say, "Oh, it's a Word document, so I need to open that using Word." Yeah, no, not equations with metadata. That's this is almost spooky, Yusuf. You are ahead of the curve. It's like you almost know what is coming next. So the big setup, it might actually not be the very next thing I'm doing, but it could be very soon. I've got sound to do, then we'll get on to you. Sound. Ooh, I wanted to show you a really badly drawn diagram. Here we go. I direct you to the, well, you've seen my drawings in class. There's a reason why I'm teaching computer science, not art. When you record a sound, this thing here is the waveform, which if you've mucked around with sound on a computer, you'll recognize, right? So that's a waveform. Now, the point I'm trying to make here is that the height of it, which is this thing here, he says, drawing more pink circles around things. The height of it is one of the things that's measured when sound's recorded, and the height of it is called the amplitude. It's the volume of it. It's not actually the volume. It's the amount of gain on it. I'm almost right. I thought I knew about sound, and then I read a sound engineer's handbook and realised that I didn't know as much as I thought. And this second one here, this one here, the distance between the waves, that's the pitch. So it's whether it's very low or whether it's very high, that's the pitch. There we go. All right. So just so you know, the height of the sound wave is what's measured when you record sound. One of the things that's measured. Okay. So let's jump in and look back at this. So sound begins in an analog form. So for example, me talking here to my microphone that I've got there, it's coming from my mouth to the microphone in analog form, and it needs to be converted into digital form so the computer can do something with it. And digital form is, of course, recording it into binary. So it says there that the analog form is pure and perfect sound. I'm not exactly sure that my voice is pure and perfect sound, but regardless. Right, so here's the next thing that's really important, that when you record analog sound, the computer uses something called sampling or samples, and that means that the sound is recorded at regular intervals, okay? So the analog signals are recorded at regular intervals, and there's your 1 mark, okay, as a starting point. you've got the fact the height of the sound wave is recorded, which is the amplitude, and it's recorded, it's sampled at regular intervals. And there are three, and these are called samples. And if you ever really got into dance music, they sample things from other bands. So they'll bring things from other bands or from other that they'll bring other sounds into a sound recording, and that's called sampling. All right. Okay, three factors that impact the file size, and again, they're fairly desperate for you to show that you understand that the higher the quality of the sound, the greater the file size. The implications of greater file size are that you can store fewer sounds on a given hard drive, that it'll take longer to upload and longer to download and take longer to send. But the higher the quality, the closer the sound is to the original, right? That the more faithful it is to the original. Okay, hi-fi. The FI in Wi-Fi and hi-fi stands for fidelity, and fidèle is French for faithful. So the more faithful it is to the original. There we go. Right, these are the three things to focus on. The sample rate is the number of samples taken per second. And guess what? This is like me talking now. I've got my sample rate set, and it's recording 96 or 36,000 times per second. The more you increase the sample rate, the closer that your sound will be to the original, but the larger the file size. Okay, so the better the quality of the sound, but the file size gets larger. Then you've got bit depth, and bit depth relates to, for each sample you're taking, how good is the quality of the sample. Are you taking a lot of information or a little information? And that's to do with the number of bits that you're recording. So are you doing an 8-bit or a 16-bit recording? Are you taking 8 bits of information with each sample, or are you taking 16? And guess what? The more you increase the bit depth, the higher the quality of the sound. The higher the quality of sound, the closer it is to the original, the larger the file size. Is this all making sense? Once you get to this point, the whole thing is basically this, okay, with a few more bits of vocab that you need to learn. And the other thing is the duration is the length of the sound. Yusuf, your time is coming. There was a question last year, which was, if you increase the sample rate, does it increase the duration? Well, no. The duration of the song is how long it lasts. Whatever you do to it, it still lasts the same length of time. Doesn't matter how you record it. The recording length will still be the same size, but the recording quality and the size of the recording, the number of the amount of kilobytes or megabytes it requires to store it will increase, but the actual length of the track is the same. If you're listening to lossless audio, the tracks don't get longer because they're lossless. They just have higher quality. They've got higher bit depth, higher sample rate. All right, so that is sound done and dusted. I'm hoping that makes some kind of sense. We've got 16 on board, which is great. Do say hello. Right, now we're into Yusuf. Your time has come. This is something that they have newly introduced for you guys, especially, and this is calculating file sizes. So if you've made it this far with your head intact, this bit is actually quite easy. You see, your time, Yusuf, would come. You have waited your entire life for this historic moment when you predicted the future successfully. So this is the, well, I would say you are more than special. I think that this is a moment to savour. Enough of that. So these are the equations. They're not anything like the physics equations you've got to do, which I have had a look at, and they are quite mean, although they do give you the equations sheet, to be fair. I think they're doing that for you this year as well, aren't they? So you might be asked to calculate the size of a sound file, the size of an image file, and the size of a text file. Well, the thing is, right, once you understand that sample rate belongs to sound, and that color depth belongs to images, and that character stuff belongs to text files, then it makes more sense. So, and that's the point, isn't it? Once you understand that bit depth belongs to sound and color depth belongs to images, it's actually quite straightforward after that. Let's take the bottom one first, because that's the most obvious one, and then we can work our way from there. So let's do this guy down here, which is text file size down there. You've only got two things to multiply together: the number of the bits per character and the number of characters. So let's take this bottom one, the number of characters. So if you're trying to save an ebook with 30 chapters, that's clearly going to have a lot more words, and words are made up of characters, than writing a sheet of A4. Got it? The number of characters clearly plays a part in it, and the number of bits per character is the second part of that equation. So that will allow you to work out the size of a text file. All right. Okay, let's go and do this one, which is the image file size. Now, once you've figured out that images consist of the color depth and then the actual physical size of the image. So how many pixels is it across? How many pixels is it down? How many pixels are we dealing with? And then you multiply that by the color depth, which is the number of colors that you're recording, okay? And the more colors, the longer those binary numbers, and the more space you need to store it. And then lastly, we have got sound file size, and that is sample rate. So how many times a second are you recording the sound? The duration of it, how long the sound lasts, and the bit depth, the amount of data that you are scooping up with each sample. Do you know what? That sounded like the perfect description to me. Yusuf, it is difficult, okay? But figuring out the starting point is knowing what this means, knowing what this means, knowing what this means, and I would have said that's it. Once you know what those three things mean, the rest of it kind of makes sense. But if sample rate is just a phrase that makes no sense and is making your head buzz, go back and look and see what it is. That's the difficult bit, is understanding what they do. All right? Okie dokie. Quiz time. We have made it. What time is it? 19:02. Okay. Quiz time. I think I've even got a special jingle. That's something I recorded myself, which suggests that I probably should get out more. But anyway, what unit is sample rate measured in? Isn't it great? Oh, hello. We've got decently straight in with hertz there. Should we see if he's right? It's measured in hertz. You are outstanding. I might find a new sound for next time. And we've got Pablo who said hertz. We've got Yusuf who said bits per second. What's it measured in? Okay, that was the key thing there. And you've got hearts, which is good. I like hearts. It sounds slightly more friendly than hertz. I need to click on here. Oh, come on, just behave. Go on. Come on. There we are. Okay, what about this one? Which of the following is not true if you increase the sample rate? So don't forget the sample rate is how many times a second. Yeah, it is. Frequency is hertz. Oh, we've got, hello Hedro, how are you? We've got decent B. We've got Hedro B, welcome by the way. We've got Josh with B. We've got Pablo with B. Which of the following is not true if you increase the sample rate? Yeah, well spotted. That was quite a nasty question, that one. It doesn't decrease the quality. Josh got it right. Pablo got it right. Yusuf got it right. And Gia Bung got it right as well. And I think, I'll just scale you with an organ. That'll probably work. Right, what about this one? What is meant by bit depth, do we think? What is meant by bit depth? I won't torture you with that. What's meant by bit depth? Ooh, now hang on. You are welcome. Josh has said C. The number of bits used to store each sound sample. And I think Hedro has said C as well. Giabung has said C. Pablo said C. And Yusuf has said C. Well, who am I to argue with these associated genii? And that's it. Once you get that, Deason's not just gone for one C, he's gone for a number of Cs, which I think makes you all the more correct.
I got a bad feeling about this.
Well, it's not a bad feeling so much. It's more that I think you are absolutely turning a corner here. So how many characters does ASCII include? 256, 120 million, 4 million, or 10 million? Deason has come straight in with a C, or I don't know. He's full of C's. Is Deason today? And I think that was that one. Deason reckons it's 4 million. Giabung has gone for A. Ooh, difference of opinion here. What do we think? Giabung's gone for A. Aussi, je m'appelle Norfal. Ah, Norfal, très bien. Ah, je suis vraiment content que tu es là. Alors, Deason's gone for A. Yeah, I'm sure you said C the first time. We'll give you the benefit of the doubt. You are all a collective bunch of genii. So 256, okay? 4 million was Unicode. 4 million was Unicode. So you are all superstars. Right then. How about this one here? What is meant by the color depth of an image? The number of bits in each pixel, the number of pixels in an image. And a bonus point for someone who can give you the answer followed by the definition of the other one. Oh, Deason's come straight in with A. Look at that. That's speedy for you. Deason in with A. Are we agreeing with Deason? Josh has gone for A as well. Yeah, looks good to me. I am impressed. So let's see if you two are correct. Giabung, Norfel, très bien. A as well. The answer is A. Out of interest, the number of pixels in an image is more. Pablo's on it as well. The number of pixels, you talk about a sort of resolution in terms of pixels, pixels across height and width, okay? So that'd be the number of pixels in an image, which will give you a file size. All right. So the next one. Boom. Okay, question 6. ASCII uses 1 byte per character. Unicode uses how many bytes per character? That's not very cheerful, is it? So Deason has said B, 4 bytes per character. Is Deason correct? He's the fastest with the answer. Norfel doesn't know. Norfel doesn't know. I appreciate your honesty. Shall we see? Shall we see what the answer is? No one else has come up with anything else, so let's go to it. It is 4 bytes per character, which means that we should take back most of the things we've said about Deason. Maybe not all. Okay, what about this one? Which of these is not an example of image metadata? Metadata. Camera model, color depth, or bitrate? God, Deason's in fast, isn't he? Sample rate, okay. Color depth or camera model? Hedro's gone for C. Shall we see what we get? I can see Josh, Pablo, and Giabun. They're a bit slower coming through here. Josh has gone for C, Pablo C, and Gyeongbun has gone for C as well. The answer is A. It's sample rate. Okay. I've got to say, I think that's actually incorrect. But anyway, sample rate. Okay, revision ideas. Boom! We have got to the end. So, to be confident with this particular topic, make sure you're happy with those conversions. But really, before you can do that, I'd recommend being confident with these definitions here. Because once these definitions make sense and you know whether bit depth, sample rate, so you know that sample rate belongs to sounds, you know that color depth belongs to images and so on, and bit depth belongs to sounds. Once you've got those sorted out, it's a much easier thing to work out because then you can spot mistakes. I fancy that they will do a sample rate for sound, spot on. I fancy that they will do that they'll quiz you, and they will make you. I think they'll do a fill in the blanks, or they will quiz you and try and catch you out by having to take one of them out. It'll make you put a series of them together to describe how you would calculate file size. I fancy they'll do that. And they might even combine that with then asking what would be the appropriate storage device to save it on. Do you remember that from last week? Whether it's a USB flash drive, whether it's they might say what's the smallest storage device you could use, which would mean knowing the maximum file size that a CD, a DVD, a magnetic hard drive and a solid state hard drive could hold. Maybe not, but they could do that. Those registers of the CPU are looking a great deal better than they were, so that is exceptional. And just start that revision process. So guys, it's been a massive pleasure. How long has this taken? It is 19:11, so 41 minutes on the dot, and I went to the right place at the right time, which is a miracle, really. So I will, as soon as I've hung up, as soon as I've stopped talking, I will send these 3. What's this? This is number 4. I will send the 4 PDFs out, so you've got those. If you revise along with me and go through these at the same time that I'm doing it, it'll mean that we're going to end up getting to May when your exam is, having covered all of them. So it's a good way of keeping up with it. So go back through these, and I will also create some, what do they call it, bookets, so you can have a muck around with those. All right, guys, you are amazing. Thank you for being here, and I will see you at the same time next week. And have a lot of fun, but not too much. And make sure you do some work tomorrow. And I'll see you all on Thursday. Be good. Bye, 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 bye.